Hello everybody, welcome to my presentation. My name is Farouk Aichouche. I am PhD student in University of Montpellier in France. So I will talk about my paper with title Modeling and Control for Production-Regeneration Systems. So in the outline of my talk, I'm going to start by introduction. After that, I will present some idea for modeling and preliminaries. I'm going to move on to maximal principle. Then we can find optimal synthesis and we'll finish with results and conclusion. We start by introduction. In fact, many systems in industry require alternating production and regeneration mode. It's, for example, the case of the membrane or accumulator systems. So it's really important to find an optimal solution to operate this kind of systems in order to minimizing the energy consumed or maximizing the production. In this case, the most appropriate control variables is the sequence of production and regeneration cycles over time, because of the time spent in production phase bring us closer to our production goal. In this present work, the generic modeling of such systems is introduced and a cost function where a minimization of energy consumption is considered when the level of the production is feasible. So we want to focus in membrane model that share the same characteristics with production and regeneration model systems. So in membrane model and during the membrane filtration, the matter X of T is accumulated until occurring falling phenomena. After that, since it's necessary to remove this matter, a regeneration process of the membrane called back-wedge phase is needed. We considered a variable X of T describing the state of processes at time t. During production phase, we can assume that xt is growing according to dynamic x point equal fp of x, and during the regeneration, this dynamic reversed according to dynamic x point equal minus fr of x. We considered also control e that take value 1 during production and minus 1 during regeneration. Then the control dynamic can be written as the equation 1. For convenience, we define f plus and f minus. Then the dynamic of x of t become as equation number 2. Assume that the energy needed for production phase is Lp of x and required for generation is Lr, where Qp and Qr are fluxes during filtration and back-wedge typically are constants, while tau p and tau r are functions describing the way that the state affects production and regeneration phase. It is obvious that the total energy demand is the sum of the energy needed during the filtration Lp and one required for back-wedge Lr, such that the total energy Et equal to equation 3. The same way as x of the t, and for convenience, we define L plus and L minus. And the expression of total energy Et becomes as equation 4. So for a given initial condition x0, the objective is to determine an optimal strategy for minimizing Et for a given total production P star, such that the process stops at the first time Tf for which the trajectory is reached P of Tf equal to P star, where the production P of T is given by equation 6, the production dynamic is then as equation 7, and as same way for convenience becomes as 8. To summarize, we consider the optimal control as this. So we can notice as one has Q plus superior to 0 and Q plus superior to Q minus, the trajectory can be reached infinite time, taking, for instance, U equal to 1 at any time. However, it is well known from the theory of optimal control that the existence of an optimal trajectory can be guaranteed when the velocity set is convex. So, when the membrane operates in the filtration, the flow resistance according to the mass X formed, which subsequently decreases the permeable flux. We assume that the rate Fp is a positive decreasing function. When changing to backweight, the mass is decomposed and membrane's permeability increase again. Therefore, the mass detachment can be described by a positive increasing function Fr. For simplicity, we consider in this study a simple linear expression for Fr, Fp, Lr, and Lp with the parameters non-negative. So we can easily check the domain x superior to 0 is invariant by dynamic of x. According to the previous assumption, it is clearly we have AR superior to AP. Notice also that the interval 0 x max is invariant by x, and the production P of t increasing whatever is the control as 0. That domain D is invariant, and we shall consider initial condition belong in this domain. Now we apply the maximum principle. We introduce the Hamiltonian. As we know, the principle of the maximum state that for any optimal solution, you start, there exists adjoint variable lambda x and lambda p solution of adjoint system given by equation 9. The transversality condition is belong to minus of the normal to set xe. Moreover, the vector lambda p, lambda x, and lambda 0 is not identically nil and has the maximum of Hamiltonian h bar. The adjoint equation is given by 10. And finally, the transversality condition lambda x of tf equal to 0 and lambda p of tf superior or equal to 0. So we define now the switching function phi, which give the following maximization condition for E star. So we begin with the first lemma. For any optimal solution, one has the following property: lambda 0 equal to -1. There does not exist abnormal extrema. There exists T bar inferior TF such that E star is optimal for T belong is T bar TF, and lambda P is a positive constant. So we focus now on the study of singular arc locus for which switching function phi is null on a time interval non-null. For simplicity, we drop the time dependency. All x lambda point x and phi h becomes as following equation. For condition phi equal to 0 and Hamiltonian equal to 0, give the system 11. So the discriminant of the system 11 is given by delta of x, which is nil for a particular value x delta bar. If phi is nil when x different to x delta bar, the system admits an unique solution for which direct computation give lambda x bar and lambda p bar. So as lambda p is constant along any optimal solution, we deduce that phi can be nil only at isolated value of x bar. and the positive root of the polynomial is given by 12. In any case, a singular arc is possible only for constant value of x equal to x bar or x equal to x bar delta. With the delta x bar equal to 0, then the control for the trajectory to stay at x equal to x bar is given by e bar. With a direct computation and by using the expression of phi, give phi point where psi is given by expression below. So from condition AR superior to AP, that's the denominator of phi point is always positive. A singular arc x equal to x bar with x different to x bar delta has satisfied psi equal to 0. And consequently, singular arc x equal x bar is a root of nx. Moreover, when the condition AR CP minus IPCR always positive, there is exactly one positive root given by x bar. A singular arc x equal x bar is part of an optimal solution if the vector adjoint is positive, lambda p superior to 0. If we consider now the singular arc x equal x bar delta for phi point equal 0, give the corresponding value lambda x, and then phi equal 0 provide lambda p bar. Therefore, if number c is positive, a singular arc x equal x bar delta cannot be a part of an optimal solution. Now we study switching curve C. We know from previous limia that for any optimal solution, the control u equal 1 is optimal on t bar tf. Therefore, for each possible terminal state xf on 0x max, one can determine in backward time the possible locus in the px plan where the switching function change is seen. If it happens, this defines the switching curve C. To summarize, there exists an unique x bar among sets x bar delta and the root of n that belong to 0x max with u bar in minus 1, 1, such that the adjoint vector lambda p is always positive and switching curve increasing on the 0x max. So under this assumption, we define following portion of the domain D, then the feedback control optimal is to applicate equal to 1 if xp belong on the plus, and equal to u bar if xp belong in C, and equal to minus 1 if xp belong in D minus. So for application, we considered a filtration system and give complete synthesis with construction of switching curve and calculate a singular arc. We find finally an optimal synthesis which have unique singular arc in D with u bar belong in minus 1, 1, and the switching curve is given by xc. Finally, in conclusion, a simple mathematical model to capture the dynamic behavior for alternating process is designed. The generic modeling of production regeneration system is introduced, and a linear dynamic is proposed to express polynomial whose coefficient can be determined analytically from the parameter of the problem. The determination of the singular arc is complex, requiring the consideration of the auxiliary function, and the methodology to determine an optimal feedback synthesis in membrane system to obtain the production P star in minimum time is proposed. And finally, we will investigate extension of the results to more general class of dynamics. Thank you for your attention.